Hi, welcome back to Allen High School. We were just talking about electrochemical cells and electron movement. Now, I want you to think about this statement, and I want you to show me this statement. I'm going to be looking for the statement in your notes when I come around and do a notes check, because I want you to process that yourselves. Now, we mentioned that if E naught relates to delta G naught and delta G naught relates to K, we should be able to come up with a formula that links these two. And indeed we can. At equilibrium, E becomes 0, all right? And Q becomes K. So I'm going to put a K in place of a Q here. And if I rearrange this, I get the most commonly used formula. That would be for 25 degrees Celsius, and this would be typically for other temperatures. By far, this is the most common one you are going to use. And again, N is simply the number of electrons involved. So let's take a look at an example here. We want to calculate the magnitude of the solubility equilibrium constant for silver chloride. Now, whenever you see solubility equilibrium, we want our solid as our reactant. A few of you didn't capture this in this unit, and we want to make sure we get this. It's, wow, Dena. Oh, Dena. There we go. Solid. Don't know why I put gas there. Solid in equilibrium with our aqueous ions. That's what a solubility is. It's always the solid in equilibrium with the aqueous ions. And we want to find the equilibrium constant for that by using an electrochemical study. So, in order to determine which one of these is oxidized and what's reduced, we're going to do something like a Hess's law approach. Notice that we need silver chloride solid as a reactant. So I'm going to keep this reaction that has the solid as a reactant intact as my reduction. So I'm going to keep that as plus 0.22 volts. Okay. Now, I want silver ion as a as a product. Here I have it as a reactant. So I'm going to reverse that reaction and get silver ion plus 1 electron. And since I reversed the reaction, I'm going to change the sign of my E naught value there. Now, if I added these up and crossed off terms that are reactants and products, that would be my only one that would cancel, is that silver solid. I would indeed get AgCl going to, in equilibrium, Ag plus Cl minus, right? Electrons cancel too. And my E naught for this cell would be equal to minus 0. Wow, I think I might have a mistake here. Minus a 0. Oh, this is 80, not 88. That's why. There we go. Minus 0.58 volts. Now that negative indicates we have a thermodynamic barrier to making lots of product. So if we're not going to make much product, I expect my K to be less than 1. Are you starting to see the link? So if E naught's negative, that means delta G naught is positive. That means I have thermodynamic barriers to making product, so K should be less than 1. So if we go ahead and plug into our new formula, we get minus 0.58 volts is 0.0591 over 1. And log of KSP. So if I did my algebra right, please always double check my algebra. 10 to the minus 9.81. And I do get a K that's much less than 1. In other words, I'm not going to make much product. I didn't expect to. There are thermodynamic barriers to making lots of product. Okay? So that's how we would link all this to KSP. Any K. Now, you can do this next one if you want. I'm going to forego doing it because the K ends up being on the order of 10 to the 62, and I really think that's getting silly. I would call that a stoichiometry because 10 to the 62 to 1 is pretty much 100% in my world, but you will see them. So we'll have time to work on these in class, so I'm going to leave that as is and move on to our very quick review, summary of the language of electrons. Oxidation. Oxidation is loss of electrons. Oxidize, the species, and it's always a reactant species that is being oxidized. And be very specific. Include your oxidation number when you're identifying the substance. Reduction is the gain. Remember, oil rig, oxidation is loss, reduction is gain. This is the species that gains electrons, is said to be reduced. Again, be specific. Include that oxidation. And remember, we're talking about reactants here. The reducing agent is the species that is oxidized. It helps another species be reduced by being oxidized. Just like a travel agent helps you travel, but doesn't travel with you. Okay, now let's go on. The oxidizing agent is the one that's reduced. They're simply opposite names. And it's terminology that I think is most important. The half reaction closest to fluorine, or the most positive, wants to be reduced and hence is the strongest oxidizing agent. A voltage is a difference in potential when you have a separation of charges. And we're going to call ours the electromotive force that's measured in voltage. Our standard reduction potential table is the potential difference given is reduction half reactions between a certain half reaction and the standard hydrogen electrode, which is assigned a value of 0. The more negative a half reaction, the more the species wants to be oxidized, and the stronger reducing agent it is. Okay, so a couple more and then we'll sign off for this video. Let's see. I did the more positive one, I think. Did I do these? Sorry. The more negative, the half reaction. So let's do the positive. The more positive it is, the more the species wants to be reduced and the stronger of an oxidizing agent. If we have a half reaction that is for an oxidation, change the sign, but don't multiply by anything. Just change the sign. Okay, if reactions are added, the E0 values are added, but again, without multiplying by that balancing factor. Okay, in the next set of videos, we will begin our discussion of electroplating and calculations involving electroplating. So until then, this is signing off.